Welcome back. We have been discussing about chemical shifts, one of the most important interaction parameters in NMR. And in the last one or two classes, we discussed about the origin of chemical shifts, the reference used, and how the chemical shift gets affected, and how to convert chemical shift from ppm to frequency, frequency to ppm, and what happens to the chemical shift when expressed in ppm as a function of magnetic field, what happened to chemical shift when expressed in frequency as a function of magnetic field, and how to convert everything we have discussed in stretch. And we continue with that class from today, and we discuss more about the factors that affects chemical shift. In the last class, I did say some of the factors which affect chemical shift. For example, steric effects, delocalization of aromatics, and ring current effect, and we discussed about the anisotropy effect and resonance effect, heavy atom substitution. Various factors are there which are responsible for chemical shifts. We'll try to understand today with some example how these chemical shifts get shielded, like particular protons get shielded and deshielded, giving rise to different chemical shifts. For example, if there is a valence electron density that can shield nucleus from applied field, causes shielding. If there are electronegativity substituents which can withdraw electron away from the particular proton for which it is attached or for the neighboring proton, causing deshielding. There is also anisotropy effect which results in both shielding and deshielding. This anisotropy comes because of the anisotropy of the chemical bond. We take a couple of examples today and see what are these factors. Starting with first, electronegativity. How does it affect chemical shifts? Of course, you all know, first and foremost thing, if there is an electronegativity group attached, what it does, it causes change in the electron densities around the new particular proton because it withdraws electrons. Okay. As a consequence, if higher the electronegativity, more the electron is withdrawn, it shifts more to the downfield. Remember this point. It resonates at lower field because it withdraws electrons, causes deshielding. So this is one of the important effects of electron density substitution with different electron density substitution for hydrogen atoms. Let us see. For example, I took the example of methane. Methane, E is of course scale of electronegativity in millikan scale. Of course, fluorine is the highest. We have referred to the here hydrogen atom, here refers to fluorine. The methane, it is in the gaseous phase. We can get the chemical shift of this, no problem. Let us say I get the chemical shift of methane. All four protons are equivalent. There is only one chemical shift, that is 0.23. Now, what I am going to do is knock off one of these protons here and put an iodine. It will become CH3I, methyl iodide. Now, the electronegativity of iodine is different. It is 2.5. The chemical shift of this proton, you look at it, instead of 0.23, it shifted to 1.98 ppm. It is in delta scale. Delta scale is in ppm scale. So that means it moved to the downfield because of the attachment of the electronegative atom. Change iodine to bromine, which is much more electronegative compared to iodine. It shifts further downfield. Of course, you know, in the column of the periodic table, we have fluorine, chromium, bromine and iodine. Now, after bromine, move to chlorine. Remove bromine and put chlorine. See, now the electronegativity keeps on increasing for the substituent atom, iodine, bromine and now chlorine. The chemical shift has moved to 2.84 ppm further downfield compared to bromine substituent. Now, last you can take fluorine, which is most electronegative. Remove chlorine and put fluorine. Now make it this CH3F. Look at the chemical shift. It moved to 4.13 ppm. Starting without any substituent of electronegative atom, the methane chemical shift was 0.23 ppm. Now, as a function of substitution of different electronegative atoms, iodine, bromine, chlorine and fluorine, there is a steady change in the chemical shift, which is moving towards downfield. Remember, it started moving towards downfield and finally ended 4.13 ppm for CH3F. Now, next question is, this is because of electronegativity substituent. Another thing I want to tell you is the inductive effect is transmitted through bonds and is not only related to directly bonded protons. In this case, carbon and fluorine is directly bonded. Okay, there is CH4, you know that CH4, out of which one proton is replaced with fluorine. Now let us look at a molecule called nitropropane. What is nitropropane? The structure is, it is CH3, CH2, CH2NO2. That is the structure of nitropropane. Now, if you take only propane, we have CH3 twice CH2. There is only CH3 group and CH2 group. There is a perfect symmetry at the center. CH3, CH2, CH3, if you write, there is chemical equivalence. Okay, you know that. I will come about splitting pattern everything later, but remember there is a perfect symmetry. Now I knock off one of the protons of CH3 group and put an NO2 group. Now it is withdrawing electrons and the symmetry is distorted. Now it is no more symmetry. We have three different functional groups. One is CH3, other is CH2 and CH2NO. There are three groups now. What happened to the CH3? In the structure, we have NO2, CH2, CH2 and CH3. CH3 is far away from NO2 group. Its inductive effect is much less as far as CH3 is concerned. So, CH3 comes at high field. Then comes CH2, middle CH2, attached to CH3, in between NO2, CH2 and CH3. This comes here. And the CH2, which is attached to NO2, comes close to 4.5 ppm, around 4.5. Look at it. It has moved enormously downfield because NO2 is directly attached to this CH2 group. So, electronegativity substitution, how when it withdraws electrons, shifts the chemical shift. This is very clear from this. Now, your question could be, why NO2? What happened to different functional groups? There are many electron withdrawing groups or donating groups. Then also it can affect. Instead of NO2, you can have OH, you can have SH, you can have NH2, varieties of groups. Some may donate electron, some may withdraw electrons. Those when electrons are withdrawing groups are there, these protons move downfield. If it is electron donating group, it moves to high field. Simple logic, right? So the electronegativity substituent has an inductive effect and has a great influence on the chemical shift of protons. Next, take the same methane, which was coming around 0.23 or 0.24, whatever that. I can lengthen this molecule. See, in this, knock off one of the protons and add a CH3 group. Now it becomes HCH2CH3. Now we will concentrate on this CH2, this proton. What is going to happen? Look at this chemical shift. It moved from 0.24 ppm to 0.8 ppm. In this molecule, there is no electronegativity substituent. There is no electronegative substituent attached. But lengthening of the carbon chain also causes deshielding. As a consequence, this proton move downfield. Now lengthen it further. Add one more CH2 in between. Now look at this proton. This moved further downfield. So lengthening of the carbon chain also has an effect on decreasing of the shielding. Now consider a simple molecule chloroform CHCl3. We have one single proton in this molecule. There are 3 chlorine substituents. The number of negative atoms substituted in this is 3. I take the proton spectrum of this molecule. I get only one peak at 7.27 ppm. Now instead of 3 chlorines, I put 2 chlorine atoms and make this molecule CH2Cl2. Now what happened? You reduce one of the chlorine negative electronegative atom. Instead of 3 Cl3, you made it Cl2. So as a consequence of reduction of one of the electronegative atom, the de-shielding effect reduced. So the proton which was coming at 7.27 moved to 5.3 ppm. Again it gives a single peak because both these protons are equivalent. It gives us a single peak at 5.3 ppm. Now I'll do one thing. I'll remove another chlorine atom here and make it CH3Cl. Now you removed 2 chlorine atoms from this molecule. So electronegative substituent is much less here. As a consequence, the shielding is also much less compared to this. Now these 3 equivalent protons resonate at 3.05 ppm. Look at the effect of substitution of electronegative atoms. The number of electronegative atoms substituted also matters a lot. More the electronegative atoms here, there were 3, it shifted downfield, 2 slightly high field. There was only 1 chlorine atom shifted high field. So the effect of number of electronegativity substituents is very clear. Okay, please remember, if you have more electronegative substitutions, greater the chances of moving it to downfield. The shielding effect decreases with increase in the distance from the electronegative atom. It's another important thing. The inductive effect will not go through so many bonds. For example, takes say a fraction of a molecule, a fragment of a molecule, which is CH2Br. Something is here, we don't care. Now this CH2 attached to bromine. This gives rise to a peak at 3.3 ppm. You understand? This gives rise to a peak at 3.3 ppm. Now what I am going to do is I will add another CH2 in between this CH2 and Br. Now what is happening? The distance between this bromine atom and this hydrogen atom, this proton increased. So because the distance is increased, the influence of this bromine atom on the CH2 is much less compared to this molecule. So there is not much of inductive effect. The electronegative effect is much less here. Instead of 3.3, this proton now comes at high field, 1.69 ppm. Add one more CH2, lengthen it more, increase the length. Now this CH2 is far away from this bromine. So the inductive effect of this electronegative atom on the CH2 is even less. As a consequence, again it moved to further high field. It moved to 1.25 ppm. See the difference. Just by lengthening the substitution, the effect of the electronegative atom keeps reducing as you go far and far away from the proton you are observing. That is an important point you must remember. Okay. Now the dependence of chemical shift of CH3 group, CH3X on the electronegativity. I'll tell you how beautifully the effect of electronegativity is seen in another example. Of course, we saw CH3F. Okay, we saw that in the methane. We changed the substitution from iodine, bromine, chlorine, and fluorine, and we saw the effect of it for this methane group. Now, what we can do is compare this with similar molecules. Now, instead of CH3F, I will take CH3OH. Now, the electronegative atom substitution is O. What is happening to electronegativity of the substitution? This I call it as X, atom X. X here is fluorine, which has electronegativity of 4 in milliseconds K. We all know that. Now instead of F, if I put O, this change it from 4 to 3.5. Similarly, chlorine, bromine, iodine, we keep on decreasing the electronegativity, and finally methane, and finally we take tetramethylsilane, whose electronegativity because of silicon is only 1.8. Look at the chemical shift, what is happening now. This starts with 4.26, we saw 3.34. These three examples we saw in the one of the previous slides, and when it comes to tetramethylsilane, we took as a reference, it is 0. See, as a substitution effect, electronegativity on a group like this, depending upon fluorine, oxygen, chlorine, bromine, iodine, this changes drastically. As a consequence, the chemical shift correspondingly keeps on shifting to high field. If you go in the order of decreasing electronegativity, it goes to low field if you go from left to right to left in the order of increasing of electronegativity. Okay. Now, another important factor is mesomeric effect. You all know what is mesomeric effects in basic chemistry. I don't have to explain that. Now consider an example of one molecule where we have an electron withdrawing group and also another molecule where we have electron donating group. Okay. This start with a simple molecule. What is this? C2H4. C2H4 is ethylene. I think it is molecule ethylene if I am right. Now all the 4 protons of this molecule are equivalent. Look at it. There is a symmetry for this molecule. There is a symmetry along this axis. There is a symmetry along this axis. So because of this axis, these 2 protons are same. These 2 protons are same. If you go along this axis, this is equivalent to this. This is equivalent to this. All 4 protons are chemically equivalent. As a consequence, how many peaks we should get? We will get only 1 peak, which comes at 5.29 ppm. Remember, it comes at 5.29 ppm. Now, we add one ketone group. What is a ketone group? It is C double bond or CH3 group we add. Knock out this proton. Any of them you can take. I took an example. Knock out this proton and put a ketone group. Now this molecule is methyl vinyl ketone. Okay. Is there a symmetry for this molecule? Now compared to this ethylene, look at this molecule. The symmetry is broken because of the addition of this group. And this is electron withdrawing group. What happens? When it withdraws the electrons, it causes de-shielding. So the peaks start moving downfield. You understand? Peaks start moving downfield, that is at higher chemical shift value. So instead of 5.29, now they come at 3 different values because they are non-equivalent. But you see none of them are around 5.29. They have come drastically. This proton, because which is close to this, goes at 6.27. This is 6.3. This is at 5.9. None of these protons have remained at 5.29 ppm. Remember, they all have moved to downfield because we have an electron withdrawing group. We will do one more trick now. Instead of electron withdrawing group, let us put a electron donating group. What happens? You put OCH3. What is OCH3? Methoxy group. It will donate electron to this double bond and increases the electron density around the protons. Look at this one. The moment you put it, again, you have broken the symmetry by substitution of OCH3 group. Look at this. When you put an electron donating group, the shielding became more. It is instead of, unlike in this molecule, instead of moving downfield, in this molecule, the proton started moving high field. Remember, instead of 5.29 ppm of ethylene, these protons started moving at 3.74 and 3.93, much higher than 5. Of course, there is a value for this also. I didn't write down because all the 3 are non-equivalent. We have 3 different protons. We have the chemical shift for this also. I have not mentioned. Don't get confused. There are 3 peaks for this also, non-equivalent. So, but remember, all 3 have moved to high field now. This is because of mesomeric effect. So, when electron withdrawing group is there, it causes de-shielding. The electron donating group is there, it causes shielding. This is the important point you must remember. The same mesomeric effect let us see in the ring system. Let us take aniline. Aniline, you know the structure? C6H5NH2. Now, what is the resonance structure of aniline? Which tells me, if you go through the resonance structure, the electron densities are more at ortho position and at para position, and it is less at meta position. This you all know from mesomeric effect, how the charged electrons start moving here in this ring. If you look at the resonance structure, these ortho proton, of course there is a chemical equivalence because of NH2. This proton and this proton are equivalent. This proton and this proton are chemically equivalent, and this is one different. So there are 3 different types of protons. Because of the charge density situated more at ortho and the para positions, these protons come at high field. They move to high field. Whereas the meta protons shift to down field. You understand? This is the mesomeric effect of an electron donating group in a ring system. This is clearly the molecule structure. What is this peak? One of them is a chloroform. Don't worry. 3 different groups are there. You can identify 3 different groups. The analysis part will, when we come to that later, we will discuss. But remember, there are 3 different groups. As I said, 2 of them are high field corresponding to this, and this one is the next one, and these 2 come to the down field. Okay, from the intensity pattern also we can understand. I'll discuss that later. So instead of that, aniline, go to nitrobenzene. What is the difference between these 2? In the case of aniline, NH2 is a donating group. Now, in the case of nitrobenzene, NO2 is an electron withdrawing group. What do you expect now? The phenomena will be reversed. So, the charge density will be less at ortho and para positions and more at meta position. As a consequence, these 2 protons move downfield, and this moves downfield, and these 2 moves relatively high field compared to this. Again, there is symmetry for this molecule. These 2 are equivalent, these 2 are equivalent, and this is different. So there are 3 different types of protons. Okay, same. The phenomenon as far as the where the electron charge are residing in this molecule is opposite of aniline. So the peak pattern will be different here. Okay, look at this one. This is meta comes here, ortho and para comes here, unlike in the other case. So another thing is about ring current effect. There is another important phenomena called ring current in aromatic rings. You all know in the benzene and other things, if you take, there is a ring current. That is because there is a electrons that are moving around in the ring generates a magnetic field. How does it generate magnetic field? We all discuss in the chemical sheet. Moving electron produces magnetic field, right? So that magnetic field will be against the external field. This also we discussed. Remember, when we discussed the chemical shift, we discussed this point. This magnetic field that is generated by moving electrons is opposite in the direction of the external magnetic field. As a consequence, what is going to happen is there will be shielding and deep shielding areas. Remember, if you can trace the lines of force of the magnetic field emanating from the center of the ring, go back, and it can come like this and go back, or it can come like this. So, and in the then when such a thing is going to happen, take a plane of the benzene ring like this. For example, it starts like this, come back like this, and start like this. So when the starting from the middle of the plane of the benzene ring, The lines of force start emanating like this and come back. So you can now you have it. If you go understand more about the benzene ring current, which I don't want to go into details, you will understand there are de-shielding and shielding zones. The just above and below the plane of the ring, it is going to be shielded zone. It is written plus. Okay, plus means shielded. Just in the plane of the ring, protons are de-shielded. Look at this one. Protons above and below the ring are always shielded. Protons in the plane of the ring gets de-shielded. So if I take a ring system of a molecule, if somehow the proton, because it's a substitution or attachment of another group, comes and sits above this ring, it moves to high field because it gets shielded. If I have a proton just situated in the plane of the ring, then what happens? It moves downfield. This is exactly what happens. The reason why, if I take the aromatic protons in a plane like this, okay, all the protons that are situated in the plane of the ring, generally the aromatic proton comes between 6 to 9 ppm. Please remember, the chemical shift of protons, the aromatic ring, which are sitting in the plane of the ring, always resonate between 6 to 9 ppm. Important point. Next, I want to quickly introduce about what is called magnetic anisotropy. Effect of magnetic anisotropy. You all know, because of the magnetic anisotropy, sometimes it so happens how the charge is situated. You can find out. Of course, this is with the ring current effect also. You can look at the molecule like aniline. Look at a bigger molecule like this. Now there are protons which are projecting inside this cavity like thing. Here also there are protons that are projecting inside. There are also peripheral protons here. This is the aniline molecule. Look at this one. The protons which are projecting outside, this one. This comes at very much downfield, nearly 11.75 ppm, much smaller. Look at this proton which is inside this. Here it is more shielded. The shielding effect is much more here. As a consequence, this proton comes at minus 14 ppm. Remember, much higher than the TMS. TMS is 0 and much higher field than TMS. This is much lower field than. See, the chemical shift difference between the internal proton and the peripheral proton, if you take, it is nearly 25 ppm difference. That is small value, just because how the charge is distributed inside and outside. Same thing in the case of aniline. The internal protons comes at minus 2.99 ppm and the peripheral protons comes at 9.28 ppm. Remember, internal protons goes nearly 3 ppm beyond TMS. 3 ppm beyond TMS it will go. That is the important point you must remember. Okay. Similarly, you have a Kekulé structure. You look at the protons internal, which comes at 1.45 ppm, and protons on the outside peripheral is at 7.94. Not so much drastic change like the previous two molecules, but still the difference of interior protons and the peripheral protons chemical shifts are obvious here. Consider a molecule like this, something that these two protons, the structure wise sitting above this ring. That's what we said. Shielding and de-shielding we discussed. When the protons are sitting above the plane of the benzene ring, it gets de-shielded, I said. Or in the plane of the ring, it gets above the plane shielded. In the plane of the ring, it gets shielded, de-shielded. That's what I said. Now these two protons are sitting above this plane of the ring. Consequence, it comes at 7.27, whereas this proton comes at minus 0.51 ppm, whereas this ring protons comes at 7.27 ppm. See the difference. These two CH2 protons sitting above the plane of the ring gets shielded so much, goes beyond TMS, and these ring protons comes at 7.27 ppm. Of course, similarly, another example you can see what happened to the protons which are in the ring and above the ring. These two come above the ring and comes at 0.3 ppm. These two protons, as far this ring is concerned, is in the plane and it comes at 2.6 ppm. So another very beautiful comparison is aromatic and anti-aromatic aniline you take. In one case, see for example, CH3 comes here and aromatic proton comes here. If you take anti-aromatic, CH3 comes downfield, whereas aromatic protons comes high field. Gets completely reversed. Remember, aromatic and anti-aromatic protons, their appearance of the chemical shift gets completely reversed like this. That's an important point you must remember. The case of aromatic protons, the aromatic protons always comes downfield, and CH3 and others which are substituted will come high field. Whereas in the anti-aromatic, the situation gets completely interchanged. Same way, we have to look at this molecule. This is the name of the molecule. And look at these two protons, CH3 groups, just sitting above this ring. It is heavily shielded, comes at minus 4.25 ppm beyond TMS, whereas these ring protons comes at 8.4. This is because of all anisotropy of aromatic compounds. Okay, because the ring current effect is there, the charge density is there, it is not uniform charge density, it is more at the above and below the field and less on the side, so it gets shielded above and below and de-shielded in the plane. These are all simple concepts. Okay, so in the anisotropic effect, you can all about what happens to anisotropic effect of a chemical bond. Remember, any chemical bond is inherently anisotropic. It has a direction in space. Look at the chemical bond here. What is happening if you take the chemical bond? There is an increase in magnetic field at the ends of the bond than at the center above and below this bond. This is a well-known concept of anisotropy of chemical bond. All of you know that. But then you can find out the anisotropy. If you know this one, you can find out the contribution to sigma. If I know magnetic susceptibility anisotropy, that by using a simple equation called McConnell equation. This is a very basic equation available in all the books. Read book by Popel, Bernstein, Schneider and Bernstein, and many other good book on NMR. Basic book will explain to you about the McConnell equation, how to derive and everything. And that is not the important point for us. Just to tell you, the anisotropy of this bond can be there, and depending upon where you are seeing this bond sitting, whether here, here or here, it varies with the function of angle theta. And now, simple example for a CC bond, if you are sitting, let us say, just exactly above the CC bond at the center, 0.3 nanometer away at theta equal to 0 degree, then delta sigma turns out to be 0.14 ppm. Whereas if you go along this CC bond, when theta is equal to 90 degree, same 0.3 nanometer distance, delta sigma becomes minus 0.28. Remember, of course, we know the value of susceptibility anisotropy of CC bond, which is well known, available in the literature. So now what you can do is, these two extreme values, theta equal to 0, 90, we knew. We can calculate knowing the parameters. Because R is known, 4 is known, pi is known, delta, this difference between this is known. Where is the angle theta and calculate what is delta sigma. Very simple. Now as a function of theta, you can plot it. What happens for a single bond, CC bond? What happens to a C double bond, C double bond? And what happens if you take a triple bond? Interesting things. You know what happens? In each of these cases, as a function of theta, if you use McConnell equation and plot the charge densities, you will see that in single bond and double bond, just above and below that bond, protons in this region gets shielded. Just in the plane of this, or in the axis of CC double bond or CC single bond, in the axis of this bond, this charge density is such that it gets de-shielded. Please remember, when I am talking about single bond and double bond, triple bond of this type of molecule, the single bond and double bond, just in the above and below the bond, protons, if they are situated, it gets shielded, but in the axis of the bond, they get de-shielded. But in the case of the triple bond, interesting thing happens, it gets reversed. Just above and below the triple bond, the protons get de-shielded, or in the axis of the bond, it gets shielded. It's a very, very striking difference you see for a triple bond compared to for single bond and double bond. As a consequence, we can see a lot of stronger anisotropy effects in this type of molecules. Similarly, so in a simple logic, I tell you what is going to happen. If I take the aliphatic groups like this, if I have a triple bond structure like this, like acetylene like this, C2H2, in this triple bond above and below protons get deshielded and acetylene comes much downfield, whereas in C2H4 and C2H6, okay, ethane and whatever that alkanes if you take, in this bond axis the protons get deshielded, above and below the bond shielded. As a consequence, C2H2 ethylene, I'm sorry, C2H2 ethylene deshielded more, it comes around this ppm, 2 point, close to 3 ppm, whereas C2H4 and C2H6, because if you are going in the axis of the bond, they have different chemical shapes. So this is what I just wanted to see. This is how the acyclic proton shielding and deshielding can be explained. So we'll stop here. We'll come back and continue later.